So let's take a look at mass spectrometry here. And you'll notice we're using the word spectrometry, not spectroscopy. As mentioned earlier, spectroscopy is reserved for probing a molecule with light, with electromagnetic radiation. And that's not what we're doing here with mass spectrometry. We're actually going to look at a molecule with a beam of electrons. We're going to hit it with a high intensity beam of electrons here. And the goal is to knock an electron or sometimes electrons, but we'll look at specific cases where we knock one electron out of a molecule. That's going to leave the molecule both with a positive charge, but also with an unpaired electron somewhere. So having a positive charge, we'll call it a cation. Having an unpaired electron, we'll call it a radical. Overall, that makes it a radical cation. An electron weighs just some small fraction of an AMU, so this really hasn't lost much for mass. So your radical cation here has the same molecular weight as your original compound, so we call it the molecular ion. So we'll also sometimes call it the parent ion, as we'll see in a little bit that it's going to give way to the parent peak. So when we hit a molecule and knock an electron out here with this beam of electrons, we're going to make it unstable as well, and it might actually break into fragments, as we'll see. But you're not just doing this with one molecule, you're doing it with a zillion molecules. So some will stay together potentially, some will break into this fragment, some will break into that, and we'll find out that the more stable the fragments it can break up into, the more those fragments will form, and it'll give a higher intensity peak on the mass spectrum. So let's take a look at some of these possible fragmentation patterns. If we look at the original molecule here, we often classify carbons based on how many other carbons they're bonded to. So this would be considered a primary carbon, being only bonded directly to one other carbon. This also is a primary carbon, and this is a primary carbon. But this one being bonded to 2 carbons would be considered secondary, and this carbon bonded to 3 carbons would be considered tertiary. And we'll find out that our alkanes often fragment in between the 2 most substituted carbons, if there's 2 most substituted carbons, and that's going to be the case here, and that would be fragmenting right here between the tertiary and secondary carbon. So let's just envision for a moment that in this molecule, so we're going to redraw it, and we're going to draw the fact that that bond is made up of 2 electrons. Well, we're going to knock one of those electrons clean out, so he's just gone. So I'll cross him out there. And so what you're left with is a couple of different fragments here. So, and one's going to be a carbocation. So typically we make the more substituted side is more probably going to be the carbocation, being more stable that way. And the less substituted side will end up being the radical. And so that's how we get these 2 fragments I've got depicted. So off to the right here. Cool, so it turns out more substituted carbocations and more substituted radicals are more stable, and that's why we broke between the most substituted carbons with our alkane here. Turns out the cation is what we'll actually detect in our signal here, and we might call this an M-29 signal here, because we're losing this ethyl group as it broke, and an ethyl group weighs 29, but we're not going to see it. It turns out you've got to be charged to be visible in mass spectrometry. We're actually going to accelerate charged particles toward the detector, and we do that with a magnetic field. We can deflect them into the detector, but a magnetic field will only operate on a moving charged particle. So this radical down here that is not charged will not be detected at all. So only positively charged fragments, it turns out, are we're going to see in our mass spectrum here. One other thing to note, if you look, everything's kind of listed in m over z, and even the x-axis on the spectrum, m over z, that's the mass to charge ratio. So m for mass, z for charge. The peaks we're going to look at are largely only going to have a +1 charge, so mass over +1 equates to mass. So keep in mind, we'll be treating this x-axis largely as mass, but keep in mind you should know it as mass to charge ratio formally. So if we look here, we found out that our molecular ion here had an m over z of 42, of 72, and we can see that right here, so on our mass spectrum. So you look at another thing called our base peak, and the base peak is just the overall tallest peak on the spectrum, so, and it's going to be given a relative intensity of 100%, and everything else is kind of relative to that, that base peak. Sometimes your base peak and your parent peak are two different peaks, but you should remember that your parent peak's for your molecular ion, it gives you your molecular weight. Your base peak is just the overall tallest peak on the spectrum. So notice also our M-29 peak that we talked about over here. So it itself has an m over z of 43, and if you notice, our base peak is corresponding to that 43. So our base peak actually is this secondary carbocation that we've labeled the M-29 peak, the loss of an ethyl group. So if you're interpreting some mass spectra, first thing I recommend you do is actually find your parent peak. So, and again, your parent peak might, I should say your parent ion might fragment into smaller pieces, but it can't form any larger pieces than that. So if you go to the far right of your spectrum here, so usually the peaks are going to appear in clusters due to some isotope effects and stuff like this, but look for the tall peak in that cluster, and that's your molecular ion. And so for this compound, we see it's at 86, and indeed, hexane has a molecular weight of 86. So for the compound on the right here, we'll go to this cluster of peaks all the way down here, and the tall peak in that cluster, if we look, weighs 93. And that's a number that's going to stick out at us. Anytime you see an odd numbered molecular weight for your molecular ion specifically, that tells you you've got nitrogen in your compound. And specifically, it tells you have an odd number of nitrogens, in this case, 1 nitrogen. Technically, if you have 2 nitrogens, you'll come back out with an odd molecular weight. I'm sorry, an even molecular weight, but with 3 nitrogens, you go back to being odd. Well, most of the time, you're either going to be dealing with 1 nitrogen or none. Every once in a blue moon, some professor will slip in a couple there, 2 nitrogens, and get back to an even molecular weight, but it's not common. And the key here is that the only way you come out with an odd molecular weight is if you have an odd number of nitrogen atoms. It's just kind of a pure coincidence here. In mass spectrometry of organic compounds, unless you have nitrogen, you can never get an odd molecular weight. It's a beautiful thing. So when you get that odd molecular weight, right off the bat, you know you've got nitrogen in your compound. So again, find that parent peak, for at the very least, get your molecular weight of your compound, and if it's an odd number, bonus, you know you have nitrogen in your compound as well.